First, I just post the quiz 4. Okay, yeah. So this morning I post our quiz number 4. Yeah. And in order to answer those 10 questions well, you need to be familiar with our Module 3, Part C and D, the content, and the Module 4, Part A and B. Yeah. A and B, yeah, the content. C and D and the Module 5, A and B, I put in the quiz 5. Quiz 5. Okay? Yeah. And there are several questions. So in the notes, I talk about those questions. But if you're not familiar with the notes, that it could be hard for you. Yeah. The last few questions. Yeah. All right. Yeah. So let's look at the problem number 13. Merge two sorted arrays. Here, for the merge operation, it's simple. Yeah, it's pretty simple. Yeah, all right. But we want to find a good solution. The good solution. Yeah, actually, that solution. Later we can see that solution is optimal. That solution is optimal. Yeah, although we will not prove it's optimal. Yeah, but we can see from some different angles, we can see, so they are close to optimal. Yeah. All right. Why take a different view? Yeah. Yeah. Because we want to use our old experience to get some new. We modify our old experience and get some new idea. Yeah. Yeah. So we have to base on our old experience. Yeah. Yeah. That would be easier. Yeah. Here, the old experience is insertion sort, insertion operation. That's our old experience. So last time, I said one important property for the insertion operation, because the order information is very useful for the insertion operation. Order information. Yeah. Here, when we merge two ordered arrays, we should take advantage of the order information. Yeah, that's important. Yeah. So you can see there is some relationship. Yeah. Insertion operation and our new operation, there is some correlation. So we want to explore. Yeah. All right. So let's start with our insertion operation. This is our insertion operation. Yeah. Because in our insertion operation, the given array is ordered, ascending order. Then we do comparison. This is V. Yeah. So we compare V in sequential order. It's not a binary order. Yeah. It's not a binary. Our standard insertion operation, we compare V with the elements in the ordered array in the sequential order. Yeah. Why not binary order? Why not binary order? The reason is because we need to shift a position. Yeah. If you do not do that shift operation, then binary search you will do faster. Yeah. But we need to do shift operation, so then you have to do this sequential way. Because shift, you cannot jump. When you do shift operation, you cannot jump, right? Yeah. You have to follow the existing order to shift element one by one to its right, sequential way. That shifting operation, that forces you to run the standard insertion operation in given order. in the given order. Yeah. Yeah. All right. So here, we need to use the given order. Okay? All right. We're familiar with the insertion operation, but here, can you expand your view of insertion? You're familiar with the insertion, but can you expand a little bit? Expand your insertion view to fit the merge view. Yeah. So our new problem, we want to merge two ordered arrays. So we want to connect old understanding and the new understanding. We want to connect them. Yeah. How to connect them? Yeah. Here, can you imagine that V single element as one element array? Yeah. You just treat that single element as one array, special array. One element array, can you treat as ordered? One element is ordered. Yeah. If you treat that one element as ordered array, do you just merge two ordered arrays? Yeah. Here you can see insertion operation is just a special case for the merge, general merge operations. Yeah. That kind of connectivity. So you can borrow the insertion step, the implementation, but you need to expand it to solve the merge problem. Yeah. That's the idea we want to implement. Yeah. Yeah. All right. Yeah. So one element ordered, but we expand. So this time, that one element ordered array, we expand it to an ordered array with multiple elements. Another ordered array with multiple elements. Then, that's a typical merge situation. Yeah. All right. So the new interpretation, two sorted arrays are combined to get a new sorted array. Yeah. Okay. So the new view, merge two sorted arrays for a new sorted array. Yeah. Okay. Yeah. Yeah. All right. So the merge. That merge, we need to address the details, all the details. Okay, all right. Apply new merge view this time. Yeah. Yeah. Insertion, the size of two arrays, 1K, one is 1. Yeah. Yeah. That's special case. Yeah. All right. It's not balanced, right? Yeah. It's not balanced. Remember, when we have chance, based on our experience, when we have chance to distribute our data, we should use a balanced way, right? Yeah. Or if we recall adversary argument. Remember last time I talked about adversary argument. How to fight against a smart adversary. You split your data in two balanced cases. That's the best way you fight against a smart adversary. So we can use that understanding here also. Yeah, yeah, yeah. Because unbalanced data distribution may cause poor worst case problem. Poor worst case. Yeah. So we want to avoid. Yeah. All right. To improve performance for the worst case. So we apply that balancing principle. Try to balance our data as much as we can. Okay? Try to make two subarrays of equal size. Two subarrays. When you split your data, you try to make even split. Then you can avoid worst case. This merge sort, one big reason people choose merge sort, because it can avoid bad worst case in sorting. That's its most prominent property. It can avoid worst case performance. Yeah. If we recall, is the selection sort can avoid very poor worst case efficiency? Cannot. N squared. Okay? Bigger of n squared. Bubble sort cannot. Insertion sort, can insertion sort avoid worst case problem, bottleneck? No. Also n squared. Bigger of n squared. Okay? Yeah. The merge sort can avoid. Yeah. The merge sort, you won't see n squared worst case. You won't see. Yeah. The reason is here because we split our data evenly, so we avoid the worst case. Yeah, so you will see. Yeah. Yeah. All right. C.2. Now we want to understand the details of the merge operation. Yeah. All right. So let's look at the first, before we work on the merge details, first let's look at how to achieve balanced subarrays. Yeah. Pretty straightforward. Yeah. Pretty split in the middle. Okay? Do even split. Whenever we merge two subarrays, we make them of equal size. When we do divide and conquer, we split the current array into two subarrays with almost equal sizes. Almost. It may not be exactly the same. Okay? Where you have all the number of elements, you cannot split evenly, right? Yeah. So one subarray has one more element than the other, that's fine. Close to even split. Yeah. All right. In that way, you can avoid worst case. Yeah. Here I use this diagram. This one line segment, the length, its whole length represents original array. Yeah. So when we do divide and conquer, we split it. First we need to split into two subarrays. So we make even split, almost even split, somewhere in the middle. Yeah, that's easy. Yeah, that's easy. Yeah. The next round, yeah, you have two subarrays. When you work on each subarray, you split, you divide, split even as possible in the middle, and so on. Yeah, yeah. And keep doing this even split like this. Okay? But you need to stop somewhere, right? Yeah, yeah. So your subarray becomes smaller, smaller. Yeah. Think about when your subarray has one element, you cannot split anymore, right? Each subarray contains only one element. So you have to stop the split operation. Yeah. All right. Then you need to start merging. Yeah. After that, now you can merge two adjacent subarrays. Because one element array, it's ordered, right? Yeah, it's ordered. Okay. You just merge two adjacent ordered subarrays. Yeah. So the first time, one comparison, you can get it. You can merge two adjacent ordered subarrays. Yeah. So you get you get a larger ordered subarrays. Yeah. The first round merging. Okay. Then second round merging. You also merge two adjacent ordered subarrays. How to merge, the merge detail, we will get there after this slide. Yeah. We will work on that detail. Yeah. Here we just assume we already have the merge operation. We just merge two adjacent ordered subarrays. Yeah. All right. All right, yeah. So then keep doing merging like this, round by round. At the end, you merge all the subarrays into this one big ordered array. The whole array is ordered. That's the idea. That's the merge sort. So you can see, if you can do this problem number 13, just to merge two ordered subarrays, then you can apply this basic operation. You can do the merge sort. That simple. Okay? Yeah. So the merge sort. Yeah. Hope it can avoid poor worst case performance. Yeah. Yeah. So we will, later when we do analysis, we will see the worst case performance efficiency, big O of n log n. Big O of n log n, worst case. Best case also big O of n log n. Worst case also big O of n log n. Average case also big O of n log n. Yeah. Although the constant could be different. Yeah. Because big O, there is a constant inside, hidden constant inside. Same category with different constant numbers. Yeah. All right. Yeah. So we need to learn the details of the merge step. Yeah. All right. So here, let me use a simple diagram to let you see the details. Yeah. Yeah. Here, many times drawing diagrams use your visual capability to understand the problem. Very useful. Yeah. For example, for this midterm, I gave you several questions, finding second largest to second smallest, at least 3 such questions. Yeah. Many students, when I did the grading, I try to understand their ideas. Very messy, okay? So very, very messy, yeah, yeah. So that's one reason my grading was so slow, yeah. Because I need to understand all the details, from the solution of the students. Yeah. I try to understand, read all the details. Those students, most of them, they didn't draw diagrams. So then it's hard. They just write, do comparison here, there. Some students drew the diagrams, then do better. So those students did better by drawing diagrams. But many students, they didn't draw diagrams, then they made a lot of redundant comparisons. Because we know x1 less than x3 already. But in their steps, they still would compare x1 with x3. We already know x1 less than x3. Why you do some redundant comparison? Because you cannot keep track of your data, right? You get lost. Quite a lot, more than half of students, they get lost. They cannot keep track of the data. But when we draw diagram, we can keep track of, right? Visually, when we see, we know x3 already greater than x1 already greater than x3. Why we need to do comparison, right? Yeah, yeah. So here, learning from this experience, you may need to frequently draw diagrams to help you understand your data. So you have a visual way to understand your data, right? Yeah. Here, we draw diagrams. So we use our visual way to understand our data. Yeah. All right. First comparison. Let's compare the minimum in the first subarray with the minimum of the second subarray. One comparison, you would get a smaller one element. That element should be in place, right? Because that's the overall minimum. The overall minimum must be in place. Yeah. So after one comparison, here let's use 0. represents the minimum of those two elements, A0 and B0. Okay? Yeah. Max 0 represent larger one between A0, B0. Okay? All right. We know main 0 should be in place in our destination array. Yeah. So this array, we put an empty array holding all the elements that are in place from the given data. Yeah. So one comparison, you put one element in place. Yeah. All right. Then that max 0, still you need to do further comparison using that max 0. Yeah. But here we consider case 1, max 0 corresponds to B0. So the next comparison you should do that max, because that's the current because now you recovered, you get to the typical situation. Yeah. So after that, you go back to the original situation, right? Yeah. So we just keep doing that. Okay? Keep doing that. All right. So this time, min 1, that's the element in place. So another comparison, you will put another element in place, and so on. How about we keep doing that, right? Every time we do one comparison, we put one element in place. Okay? Yeah. All right. Yeah. Now, let's look at merge two sorted array, the worst case in place. Yeah. This time, because we have best case and worst case, right? Yeah. So we want to look at how many comparisons we need to do for the worst case. Yeah. The maximum possible number of comparisons for the worst case. Yeah. So, right, 2k minus 1. The maximum number, yeah. So the first subarray, we have k elements. Yeah, good. Yeah. For the first subarray, we have k elements. Second subarray, we have k elements. Okay. Now we want to get the maximum number of comparisons, but we know the last element, we do not need to do a comparison. Last element automatically in place, right? So the maximum number of comparison we can do 2k minus 1. Okay, 2k minus 1. Yeah, that's the worst case. That's the worst case. Yeah. All right. Yeah. All right. All right. Yeah. Yeah. So except last one. All right. Yeah. So the number for worst case answer 2k minus 1. Yeah. Yeah. But here you can see that here these two arrays has the same size k. But in the general situation, sometimes we need to merge two ordered arrays of different sizes. That's possible, right? Yeah? Yeah? Yeah. Because we may need to use this merge operation, not necessary in the Mergesort. Yeah. In the real world situation, sometimes we may need to merge two ordered arrays of any given sizes. Okay? Yeah. So this time we want to get a formula for the general merge step. Yeah. So first subarray m elements, second subarray n elements. Okay? Yeah. Mn, any positive integer. Okay? Yeah. In this situation, worst case, what's the maximum number of comparisons? Yes, m plus n minus 1. Total number of elements, minus 1. The last one, no comparison. Before the last one, each one, you need to have one comparison to put it in place. So the formula is m plus n minus 1. Yeah, that's our first formula. General case formula first. but it's for the worst case formula. Okay? Yeah. Next, let's move to the best case. Yeah. Let's do the same thing. Yeah. This time, let's just do directly for the general merge step, but this time for the best case. Can you imagine under what situation we would get the best case? Try to see that. Minimum number of comparisons. You can get whole array ordered, yeah, but your input should have some special property. Think about that. Yes, smaller number of m and n. Yeah, so your intuition is good because we have two positive integers. Usually one should be smaller than the other. Yeah. And he says the best case, the number comparison should be the smaller number of these two positive integers, m and n. That's the minimum of these two positive integers. Yeah. How can you see it? We want to understand why it's true. How can you see it? What special case would allow you to have this situation? Yes, yeah. You get the main point. You get the main point. Yeah, let me explain your observation to other students. Yeah. All right. Yeah. So here you can see when we do comparisons, we pick one smallest element in first subarray, another smallest element in the second subarray, yeah, smallest available, let's say available, yeah, because after we put it in place, we eliminate it, so not available, okay? So let's consider the current available elements. When we look at the current available elements in two ordered arrays, we always pick smallest element in each subarray and do comparison. Okay? All right. Yeah. Then, the main observation, in order to get the best case efficiency, you want to get a situation that you can put the remaining elements in place without comparison, right? Yeah. Without comparison. If you can do that, if you can put the many elements in place without comparison, that means you use fewest possible number of comparisons. Okay? Yeah. All right. How to maximize the number of elements you put them in place? One situation, one typical situation. The smallest element in one of the subarrays can beat all elements in the other subarray. How about that? The smallest one is greater than all the elements in the other subarray. So you just use the first element in one of the two subarrays. You can use it to put all elements in the other subarray all in place. Okay? After that, the remaining elements, you do not need to do any comparison. You just copy them into your destination array. That's it. Copy the whole array into your destination. Definitely you want to copy more elements, right? To get the best efficiency. That should be the longer subarray. So the shorter subarray, you exhaust. You use the smallest element in the longer subarray to exhaust all the elements in the shorter subarray. That's the understanding. That's the main observation we need for the best case efficiency. Okay? Yeah. So if we do that, yeah, the strategy, try to exhaust one of the two arrays as early as possible. Okay? Yeah. 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 All right. Exhaust the shorter array. Yeah. 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 Not longer, shorter. All right. So the best case efficiency minimum of m and n. Minimum. Yeah. See? These two formulas, here you can see our typical merge step. Here, when we look at our general merge step, you need to know these two formulas. Okay? You need to do these two formulas. And I will give you several questions based on these two formulas. Okay? Yeah. First, I may ask you to apply the merge sort to sort an array with certain number of elements. But when I ask you to do it, I should let you know the best case and the worst case. Which one I like you to do? The best case, when I ask you to sort it for the best case, you need to apply this formula. When I ask you do it for the worst case, you need to apply that previous formula. Okay? No. All right, so that's the, yeah. C.3, efficiency analysis for merge sort. So this time, we want to do the calculation to see the best case efficiency and the worst case efficiency. Yeah. All right. How to see that? Derive recurrence relation. All right. Estimate the worst case efficiency first. Then we can use the similar way to estimate the best case efficiency. Yeah. The worst case efficiency. We can draw diagram. Yeah. First, let's look at this diagram. Yeah. So given an array, split in the middle. So if the number of comparisons for the merge sort on the whole array with n elements, we use this t function, t of n comparisons. We want to write the recurrence relation. Yeah. So let's do the split. All right. Yeah. Split, even split in the middle. So two subarrays, each one they should have approximately equal size. Equal size, 1/2 of the size. 1/2 of the size, divide and conquer, divide the cost is minimum, right? We split in the middle. Yeah. The cost could be ignored. Okay, the cost minimum, very little. Yeah. All right, conquer. When we conquer each subarray, here there are two subarrays, we need to conquer it. So we apply that t function on these two subarrays. T, so the number of comparisons should be, here we estimate. Yeah. Here we do estimate. Okay, yeah. T of n over 2. T of n over 2. For these two subarrays. Then, after conquer, we need to combine these two subarrays. When we combine, we need to apply the merge sort. Merge operation. That merge operation, here we consider the worst case, right? The worst case, we should use the worst case formula. Okay? Worst case, n minus 1 comparison, right? N minus 1 close to n. Here we do approximation because n minus 1, then minus 1, not easy, so we need to, keep that little detail. We need to do a little more work to keep that little detail. Yeah. So we use convenient number n, just n. Okay, yeah. Now let us write the recurrence relation in this way. Yeah. T of n equals 2 times T of n over 2, but you need a merge operation, so you need this and comparison as your combined cost. Combine two ordered arrays. You need to pay this many comparisons. All right, so now we need to solve this recurrence relation. But we just want to estimate, because here n over 2, so if you pay attention to the detail here, because n over 2 sometimes may not be integer, right? So you may need to apply the flow function. That would make the computation much harder. Okay? Here, remember here, we do approximation. When we do approximation, we do not require this n over 2 to be integer. Right? Non-integer, we take it. Non-integer, because it's approximation, right? We do approximation. So we keep that data size n over 2. Keep as is. Keep as is. Because later we do approximation. Okay? Our approximation formula not necessarily integers. Approximation a little larger, a little smaller. We only require it's close, right? So that's good enough. So we keep all the fractions. Okay, all right, for approximation. Consider a simpler case. The simpler case, here, I tried to make the case simpler. Simpler, what's that? Power of 2, right? Power of 2, simpler case. When n is power of 2, then the recurrence relation, we can simplify it. T of 2 to the kth equals 2. So the formula, power of 2. Transform by division method. Now we need to use some small technique. In order to solve this recurrence relation, we want to transform the formula. Transform. When we do transformation, remember, how did we solve the recurrence relation for the Tower of Hanoi problem? We want to make left-hand side, right-hand side similar structure. Similar structure. Here, we do the same thing. We want to make left-hand side, right-hand side, the main term should have the similar structure. Here we do division by 2 to the k. Division 2 to the k. After division 2 to the k, both sides, look at the structure. This structure and the right-hand side structure, are they similar? The structure, right? The structure, same structure. All right. If the same structure, can we introduce a new function to represent this structure? New function? All right. So let's define a new function, so we can get a better view. We can see our problem better. Okay? Let's introduce a new function. Capital G of k equals this fraction, t of 2 to the k over 2 to the k. Introduce a new function. After we have this new function there, the recurrence relation, after we use a new function, we can write the recurrence relation as simple as this. G of k equals G of k minus 1 plus 1. That's very simple, right? We just keep doing the recurrence, iteration. Keep doing the iteration. Okay? G of 1 equals 1/2. G of 1 equals 1/2. Because when k equals 0, T of 1 equals 1, T of over 2. So, k equals 1. K equals 1. Oh, yeah, K equals 1, right? Yeah, plug in K, yeah, 1/2. Yeah. All right, let's do iteration. Keep doing the iteration. Yeah. But we need to keep track of all these equations. How do you keep track of all these equations? Is there any special way that can help us keep track of all the equations without getting lost? Without getting lost? Can you observe some special property? Yeah, right. Look at K minus 1 plus 1 equals 1. Okay? K minus 2 plus 2 equals 2. Yeah. All right? If you add up these two numbers, you get a fixed number, K. So you use this one, we call it invariant, right? Invariance. Invariant property, invariance. This property can help us keep track of all the equations. Yeah. All right? So the invariant method, the size plus the constant number, you get the same K number everywhere. Okay? All right. So when you reach the bottom, G of 1, the constant part should be K minus 1. Okay? But G of 1, it's 1/2. Yeah. So you get K minus 1/2. G of K equals K minus 1/2. And we want to go back to the original function using T. Yeah. So let's calculate. T of 2 to the K equals, parenthesis, K minus 1/2 times 2 to the K. Yeah, all right, yeah. N equals 2 to the K. This 1/2, very small, we can ignore it, right? Yeah. So approximately we use K, but K is log base 2 of N. Log base 2 of N. So we get approximation, T of N equals N log N. That's the estimate. That's the worst case. Worst case for the merge sort, we need to do this many comparisons, N log N. Okay? Yeah. Yeah. All right. Yeah. You can argue, because here our N, we use power of 2. You can argue if N is not power of 2, this estimate may not be correct. You can argue in that way, yeah. But actually, we can easily see for general N, this estimate is still correct. This estimate still correct for the general N. Yeah. All right. Yeah. Yeah. Okay. Yeah. So why I can say something. Yeah. Yeah. Before I move to the next slide. Next slide, I want to talk about another special example. Okay. Another special example. Before I go there, yeah, let me explain why for general M this formula is still correct. Okay. So this formula correct for the general N case. Yeah. All right. Here, there is one special way we can see it. One special way. Yeah. Yeah. All right. We draw binary recursion trees. Here we have a recurrence relation. So we can draw binary recursion tree. Okay? Yeah. So we start, this is our starting point, T of M. We want to estimate T of M. And we want to accumulate cost. Yeah, because every time we split into 2 halves, so then another level split another half, and so on. Okay, keep doing that. Yeah, let's try to accumulate the total cost for the implementation of the whole algorithm. Yeah, all right. And combined cost, we need to accumulate, right? Yeah, the first time, yeah. So the node at zero, at the root, we have this n comparison cost. So here, we put there, all right? Yeah. The t terms, because the t terms, we get to the next level, yeah. T terms, we split. Yeah. Next level, there, when we apply the recursion, the non-recursion cost this time becomes n over 2 and n over 2. Okay? Yeah. So we only accumulate the non-recursion cost because that cost stays there without further recursion, right? Yeah. It stays there. Okay? So we accumulate. Yeah. Then another level down, n over 4, here, n over 4, and n over 4, right? Yeah. Keep doing the bottom level, n over 2 to the k, n over 2 to the k, and so on. Okay? All right. Let's look at each level. What's the subtotal cost? Each level. The top level, n. The second level, also n, right? The third level, also n. Each level, subtotal of the cost, all n. Same. Yeah. And the bottom level, the subtotal cost, also n. But you want to look at how many levels do you have? Yeah. This is, we treat as 0 level. Okay? K equals 0, top. 2 to the 0. Yeah. So k plus 1, but k plus 1, k the same, right? Yeah. Very close. We use approximation. So you can use k times n, but this k, is it log base 2 of n? This k, log base 2 of n, so you get n times log n. That's for the general case, right? Yeah. Because this time we do not require n is power of 2. We estimate. We do division, but it's estimate. Okay? Yeah. We do not require that division gives us integer numbers because we estimate close number. Okay? So this way, binary recursion tree, we can have good estimate. So we accumulate all the non-recursion costs, so we can also get n log n. Okay? Yeah. So this way, you can see we can understand. Here I use understanding, so we can understand why the worst case efficiency for the merge sort is n log n. Okay? All right. Next, I want to show you the best case. The best case. Efficiency. How to see the best case efficiency for the merge sort. How to see the best case efficiency for the merge sort. Okay? Can we just modify our recurrence equation? We change n to n over 2. Right? Every time when we split, we exhaust one subarray. Okay? That combined step n over 2, best case. So we only change this number, n over 2, from n to n over 2. Okay? Then, when we build a recursion tree this time, at our root, we have the non-recursion cost n over 2. Next level, n over 4, n over 4, and so on, right? If you accumulate each level n over 2, this level also n over 2, all the levels total n over 2, you add them up. You also have k levels, right? Log n. So n over 2 times log n. So you will get n over 2 times log n for best case. Is that still in the same category, big O of n log n? Yeah. So you can see, use this method. You can estimate the best case easily. Best case easily. Worst case, best case easily. Okay? Yeah? So it's a good estimate. Okay? Yeah? Yeah. Yeah. So now you understand for the merge sort, the best case, worst case in the same category, pretty close. Yeah. Average should be between these two cases. Right? Yeah. Average case. Okay? Yeah. All right. Yeah. Next. Yeah. So we still have about 15 minutes. Yeah. Next, I want to talk about a few homework-related questions in our next homework assignment. Yeah. Yeah. So yeah, after Wednesday's class, then I'm ready to assign you homework assignment number 2, covering second half of module 3 and the whole module 4. Yeah, because in this 1.5 modules, we have many relatively challenging problem-solving questions. Yeah. Not too hard if you understand well, not too hard. Just relatively challenging. Yeah. All right. Here I want to talk about 2 possible homework questions. You will see in homework assignment number 2. Yeah. Regarding merge operations. The merge operations, the best case and the worst case. Okay? All right. Here, I give you 2 questions, for you to think about it. All right. Yeah, because these 2 questions, one for the worst case, one for the best case. Let me just write once. Write once, but we consider these 2 cases. Okay? All right. All right. Here, the question, main body, the main part of the question. Given 3 ordered arrays, 3, not 2. Okay? 3 ordered arrays with the number of elements with the numbers of elements A, B, and C respectively. Okay? Yeah. A, B, C respectively. Okay? In our homework assignment, you will see concrete numbers. Okay? Yeah. So I will replace A, B, C by concrete numbers. Okay? Yeah. So you, all right, concrete numbers. We want to merge these three ordered arrays first run for the worst case. Two for the best case. The question, how need? So that's two of our homework. Number two. Okay? Yeah. So here, let me explain a little bit. Yeah. Yeah. So we try to do analysis here a little bit. Yeah. All right. Yeah. Because when you merge, so here, 3, A, B, C. Yeah. So here. So you have A here, you have B here, C somewhere here. So when you merge, you have a few choices, right? Do you want to merge A array, B array first? And another merge like this, right? So that's one, okay? And you have other ways, let's say A, B, C. Do you want to merge this for the first merge, B and C, okay? Then the second merge, 2, all right? Yeah. And another case, yeah, let me draw B here, A here, C here. Do you want to merge A and C first? And, B remaining second. Yeah. Here you can see we have at least, first these 3 different ways to merge. The questions, the different ways to merge these 3 different arrays. Should we get different outcomes? Different? Yeah. Some special way would allow us to do better than the other ways. Yeah. And the answer, you can look at the answer, could be different for the best case and the worst case. Yeah. Here, because the best case, the worst case, we use the formula m plus n minus 1 number of comparisons, each merge. Okay? For the best case, we use the formula minimum of m and n, right? Yeah. Different formulas. Yeah. So the answers could be different for best case and worst case. That's something interesting. Yeah. You need to.
Because it's comparing 3 ordered arrays, would the worst case be like n plus O minus 1? Because isn't the m and n the number of elements in the 2 arrays when you're talking about it? The slide shows like A has n elements, B has 2 n elements.
Don't use that generalization. Okay? Oh yeah. So yeah. So here, if my understanding is not correct, correct me. Okay? Yeah. So what he said, yeah. If my understanding is wrong, you just correct. Yeah. Remember, For the worst case, for two subarray, yeah. Here, let's say size M, size N, and a size L. How about that? Let's represent. Okay, M and L. Typically, people use that way. He, based on his idea, he wants to generalize the formula for these three worst case. A natural way to generalize. Do you think the number comparison M plus N plus L minus 1? Yeah. Yeah. Minus 2. Yeah. Some students, they feel minus 2. So, yeah. Some students, but actually still, if you change to minus 2, still not correct. Yeah. Still not correct. Yeah. Because one number you may need to add to one more time, right? And think about. Yeah. Think about. Okay. All right. So let me work on one example here to show you. Let's work on this case. Let's work on this case first. Okay. All right. The first merge, we need to do M plus N minus 1, right? Comparisons. First merge. But after the first merge, we get an ordered array with M plus N elements, right? All right. Now we want to merge two arrays, one with M plus N, another with L. Okay? So our second merge, the total number minus 1, what's that? M plus L minus 1. Finally, we should add these two numbers, right? Yeah? Yeah. Two rounds, add these two numbers, so the total for this case, 2M plus 2N plus L minus 2, right? Think about, okay? Think about. Yeah. From this formula, can you see, now, based on this formula, can you tell me under what situation you get the minimum solution? 2M plus 2N plus 1L. That 1L should be the smallest of the three numbers, right? Because that L number, do you want to make that L number, largest, yes, largest, okay? All right, so here, let's, 2M, that's 2 times N plus M plus N plus L, that's a fixed, right? The total size is fixed. But when we minus L, we want to minus the smallest number, largest number, largest number. Because we want to make the whole number as small as possible. So we want to make L the largest array of the three, longest of the three arrays. Okay, yeah? Yeah. But that's for the worst case. For the best case, we may not have this property, right? For the best case, the formula would be different. Okay? The formula would be different. See? Yeah? That's the background, okay? To give you, you need to consider, situations like this. Okay? Yeah. All right. Yeah. Just the 5 minutes. Yeah. So we will finish soon. Yeah. Here. Yeah. So here, first, in our homework assignment, I give you three ordered arrays. Yeah. So after you study, you find some rule. Yeah. Then, in the final, I may give you a 4 array question. So you need to use your 3 array result understanding to help you solve 4 array problem. Okay? Yeah. Something like that. Yeah. 4. Yeah. Because 4, you have you may have too many cases, right? If 4, yeah. So that would be, if you want to exhaust all possible, that too much work, okay? Yeah. So here, because why I give you 4 array case, because you can summarize some rule, some property from the 3 array question. 3 array question, after you solve the problem, you can get some conclusion. Okay? There is some nice property, you can take advantage. Okay? Some nice property. So then when you apply that property to 4 array question, you do not need to exhaust all the cases. Okay? Yeah. Yeah. You can just do one case because you know how to find the best case. That idea. Okay? That idea, that problem solving strategy. Okay? Yeah. So the homework experience important. Yeah. For the final. All right. Yeah. All right. So that's it. Let you go. Yeah. So we